yeah, any kind of final questions, comments? I mean, I shared the R script, so maybe that will be a base that people were trying to write your code about. But last time I remember we spent some time explaining the model as well. So it's not a, like a, Ellie, I'm just looking at you. And not some kind of easy model and simple model to understand. So as you implement, you might get into some of the details and happy to answer questions you have. So we just gonna see whoever wants to start the discussion, we can get it going.
How many like nested loops did people use?
I mean, as you all will be talking about
My
that.
last one was 3, which is like there was one step that was really slow. That's one thing. Like even I'm pulling up Professor Who's in R. Just the ability to draw over vectors in R makes sometimes it seems like the R implementation so much faster.
Yeah, but when I play with it, I didn't find it particularly faster than, because Isaac, you're saying that yours, I mean, running the Z loop, right? Like generating that part. I think you're saying that one iteration is like 2 seconds or so. I think,
it was absurd.
Yeah, running mine, I didn't find it particularly faster, but in my email, I mentioned that I noticed, I wrote it in the past. Like I didn't use the loop per se, I think, for drawing that part, but overall, I mean, my code still takes time. So as we discussed, let me just get the screen to share the model. So we're on the same page. Can you all see that? Here? All right, so yeah, like I guess Ted's question here, how many loops? I mean, we have an overall big loop in the first place, right? Like we'll have all of the iterations going through for I mean the iteration, yeah. But then within it, I guess there definitely is a loop for the Z here, and then the Z part again because of the J, like you have to go through, I think, all of the variables as well. So that, oh, I should also say because of you have to sum over all of the K, and then that might induce another loop. But for the other ones, I guess probably no loop is okay. Anybody comments? Or Ted, how many loops did you use?
I was also trying to aim for like the 3 that was in the R code, but in my brain I thought we needed to add another one for some reason, and that's when I got confused, and I don't know what part of it anymore because I haven't looked at it in a while.
Oh, okay. I mean, one thing I think, like from last week, if you didn't come, if you got the chance to watch the video, I think Isaac's code was working. It's just slow. So I think I mean, but I mean, I don't think it's particularly slower, to be honest. I mean, it's fine. I mean, that kind of model does take time to estimate and all that. But any updates from anyone about, like, say, have you run it? If it takes time, I mean, just set it to run, I guess. But then once you run it, I guess there's certain, I guess, open-ended questions here of what we're looking at, right? I mean, we're estimating a lot of parameters, obviously. Yeah, what should be like how to do MC diagnostics, for example, for this kind of model. I think that would be a good thing to talk about. And of course, if you have comments about the code itself, like, yeah, feel free to speak up. Anyone? I will stop share my screen. Anybody wants to make a comment or share your screen about what you have done? Or everybody's good, so we're gonna call it a day early.
Sorry, I'm just walking over I'm in between things I'm doing at work right now, so I can't share any screens.
Oh, it's fine. We can see the blue sky. Anyone? Yeah, Isaac?
I had one question on the, like, I guess when you do like obviously a trace plot or a autocorrelation over Z isn't super tenable. Like,
Yeah, it's
just
too many of
there's
them.
so many to do.
Mm-hmm.
And the other part of it, sorry, I guess doing the probabilities isn't helpful either because they're capped at 1. Like, would you trace by just selecting one of the probabilities?
Yeah, that's a good point. So the question is, yeah, so for this kind of model, because there are so many parameters as we have fit them here, it would just be complicated to show the trace plot and all that. So the thing that I used to do, like for this kind of model, is I just pick one to show it, and usually I just pick alpha because that's the univariate, and it was overall easy to show, I guess. But again, the capital K, because we know that's the how many latent class that you want to use. So that number also, I mean, if you bump it up, I think I used 30 in the demo in the R code. And but the thing is, if you use a large number like 30, for example, then you just like scaled up how many parameters you have. I mean, say 30 compared to 5 or 10. So that's another thing. But overall, I mean, I don't think there is an exhaustive way to show the trace plot or MCMC diagnostics overall. Maybe one thing, I mean, say, for example, if you take a look at the trace plot and autocorrelation plot for alpha, you would get a sense, I mean, if it's bad, I mean, you probably have to do like more running or anything. But if it looks good, maybe one thing to do about the diagnostics is to do posterior predictive checks. And that would go through, if we come back to the model itself, I think Isaac was asking that last time as well, like say at each iteration you get a bunch of pi, right? Pi 1 through pi k. So you can generate, you have to write a loop in this case. You have to generate the zi, right, for each observation. And then given that, you will have to, I guess, another loop here, go to generate the new xij for each observation. So you can do that as a way to do the posterior predictive checks. But then in terms of once you generate a new set or multiple sets of like simulated or predicted data, well, they're all categorical variables, so you probably have to do all kinds of tabling, looking at how the predicted and how similar, right, the predicted and the originals are to each other. So overall, I mean, it's just complicated, I agree. But this kind of model is powerful in the sense that they can jointly model a lot of categorical variables at the same time, okay? And then overall, the setup is straightforward. Like you assume that each observation belongs to a latent class, and then given that conditionally independent, every variable follows a particular multinomial distribution. Yeah, Isaac, did you have a question?
Yeah, I was gonna ask, like, because isn't the point of stick breaking, like, you truncate at some k that's way far above the number of classes you'll actually, like, it's close enough to infinity is the idea?
Yeah.
So like, what's the point of doing trace plots on like the k equals 29, 30? Or like, where do you cut off where at some point I imagine like k just doesn't become relevant?
Yeah, good point. So when I was like cleaning up the R code that I sent you last week, I deleted certain things, but I mean certain things that actually I will like track. So for example, what Isaac is asking here, we use, don't worry about the terminology, the K, like the capital K, where is it? Yeah, the capital K that we're using here is sort of like is truncated at some large number. So this kind of model is saying that I want to allow the number of latent classes to be infinity, okay? But one way to make the, I mean, in a sense that I don't know how many latent classes are. I'm gonna let the data decide how many it needs, okay? So that's the general idea. However, if you want to use a way to, I mean, one way to make the computation work is to truncate it as some large number, okay? So K, for example, like I use 30, and one thing I would do in the MCMC is to actually check, I mean, at each iteration, how many latent classes out of the capital K that are actually being used, okay? Or maybe how many of the latent classes actually are sort of populated to some degree. We have 10,000 observations in total, right? So we have 30 latent classes. So maybe you want to check like not only how many of the K latent classes are utilized. This is, I mean, overall, you can just count how many are greater than 0, right? Like you do a sum over there in that iteration. Or you can, I mean, not greater than 0, but maybe like greater than 5 or 10, just to make sure that the latent class is populated well enough. The thing is, if you look at the model, like equation 1 here, you can see that because it's conditioning on the latent class the observation goes to, right? So whenever you're estimating those theta, so this theta, for example, if it's, I don't know the variables in particular, but let's just say it's a variable, it's a categorical variable with 5 categories. So in order to estimate the theta, actually come back to here, that's probably best. If you look at how we actually are estimating the theta, we need to count, right? How many observations actually fall into that latent class, right? So the thing is, I mean, if you have some latent class with not really populated, then the estimation wouldn't be that good. Right? You don't have a lot of, like a large sample to estimate it. So per what Isaac was asking, one thing you could do, like I said, is to track across the MC to see how many of the Ks are being utilized, okay? And the code, for example, if you choose a larger value of K, it will take longer to run because you have more latent classes to estimate, okay? If you have fewer, like say compared to 30, maybe you have 15 or 10, and then it will be run faster. But the reason why you want to trace or check how many Ks or like how many of the Ks are being utilized, you're able to like say maybe adjust how many you really need, okay? Say for example, if I set K to be 30 and I check that across the I don't know, 5,000 iterations after the burn-in, I realized that almost every time I only use up to 15, then that might be a reason why you might want to decrease the value of K. I mean, one thing is, well, let it run faster, but also just do not, I mean, obviously the data does not really need that many clusters to use. But if you set K to be 30, and every time you notice that like the utilized latent classes are 30, like every time it's like that, then that might be an indicator that you should increase that a little bit larger yeah. So in practice, I mean, I think that's what people do. Like say how to set the K. I mean, K is a truncated value, and the larger the better, of course, but in terms of computation efficiency, people will like track that in their MCMC and then adjust it accordingly. Does that answer your question? It's probably a way longer answer.
No, it makes perfect sense.
Okay, yeah. I think in practice, that's what people do. Yeah. Mm-hmm. Anything else? Everybody's code is running or has run?
I'm gonna have to maybe learn from someone else's code to fix one of my loops, I think.
Mm-hmm,
Or like one of my draws. I think I just did something wrong with notation maybe.
mm-hmm, mm-hmm. Yeah, any of you, if you have your code running, I mean, feel free to upload it to GitHub, and then others can learn from that. I mean, again, I put this together mostly because I think it's a good coding exercise. I mean, the model itself, I mean, I don't know if you're ever gonna use this, but I mean, I list a way to think about how a joint model can be specified. I mean, latent class model is pretty common, I think, in many applications. And the way that I mean, the one that I showed is all categorical variable, right? But you can have actually mixed data type, that you have some categorical outcome, you have some continuous outcome, and then you can use this mixture or latent class model that any kind of univariate variable is independently follow a particular density. If it's continuous, you can use a normal or some other continuous density. If it's like unordered categorical data, like the one that I share with you, then that will be a typical multinomial, okay? But the key is conditioning on the latent class assignment. Each variable independently follows its own particular distribution. And I think that kind of setup is what makes the heap sampler feasible, right? Because you are able to, like say, sample Z, the latent class assignment, and then for any parameter about the say like the theta that we saw, that's the categorical probabilities that we're doing. But then if it's a normal, say, then in that case you're gonna have a mu, right? You're gonna have a sigma, and then there you're able to update them accordingly by counting how many observations are being classified or clustered in that class, and then you go from there. Anything else? Okay, if not, I will stop the recording.